I am again asking Mark Morris. He will present us fifth presentation.
So now you know the probability that your dike is going to foul, you need a breach model to tell you what's going to happen. And first you go to Myron because it's system risk and you want it fast, but if you want to look at it in a little bit more detail, then here we go. So I'm going to talk about some work we've been doing over the last 5 years looking at evaluating different breach models. That's the Dam Safety Interest Group breach modeling project. And then a little bit about the Simba wind dam model, which is in the States, USDA, and the HR breach, or the HR zoned breach model, which we've been developing. So what are we doing and why? I don't think I need to explain. That's covered. We need we need reliable predictions of breach, not only to calculate the volume of water that's released, but where the rate and nature of release becomes important. In the States, some years back, the Dam Safety Interest Group, which is a group facilitated by SIATI, decided that they would undertake a breach modelling project. The objectives of this project was really industry focused. They wanted to look at what breach models were out there, looking at physically based breach models, understand how they performed, which model or models might be appropriate for uptake into industry use by integration into flow models or use within flow models. This built on a number of earlier European projects that I'd certainly been working on: CADAM, Concerted Action on Dam Break Modelling, the Impact Project, the Flood Site Project, USDA, again at Stillwater, they have a long program of looking at breach and head cut, and similarly at Wallingford. Just to give you a feel for the background to this, these are the key project partners: EDF, Hydro-Quebec, Bureau of Reclamation, so on. You can read the list, and other interested groups down here. One of the rules of being a member of the Dam Safety Interest Group is that they're actually dam owners and operators, so they are looking for practical tools to use to help them in asset management. That project went in 2 phases. There was a first phase where trying to get data. This is always the problem for breach models. What field data is there? What laboratory data is there? What can be used to test and evaluate breach models? So there was a big review of the data. There was a big review of different breach models worldwide. And then in the second phase, having identified a number of breach models, it was much closer evaluation of the performance of those breach models. And then the final step down here still continues today, which is the ongoing development of breach models for practical use. In there was another activity related to how do you measure soil erodibility, and there are different processes around the world which I'll come back to. So I'll come straight on to it. The soil erodibility work was really comparing the jet erosion test with the whole erosion test. Jet erosion test developed in the States at Stillwater, jetting water at a piece of soil. Whole erosion test, squirting water through a hole to test the erodibility of soil. And there's differences between those, so there is still ongoing debate about erodibility measurements that come out of the whole, the HET test versus the jet test and so on. And there's plenty of publications if you want to read up on that. It is important because the soil erodibility underpins any of these breach models. It dictates the rate at which the breach grows. So in terms of the breach review, 3 models were identified as having good potential for future development. That was the Simba wind dam family, the American model, HR breach model, and Firebird, which was a model from Montreal Polytechnic. A long program of evaluation was undertaken using 7 sets of data. 2 of those were from the States, from Stillwater, 3 from the Impact project, and 2 case study real dam failures. It was very interesting trying to compare different expert modelers using different models applied to the same data sets. You cannot be objective. You have to look at it case by case, modeler by modeler. Hence, the results that came out of this assessment are in this form, where you've got the different models here, and this one here is the NWS National Weather Service breach model from the dam break code, and there is a descriptive measure of its performance. Firebird dropped out at this stage, and the conclusion really was that the best approach was using one or other or both of the HR breach and the Simba models. I'll go on to explain why those 2 models are different now. One of the unfortunate problems, hold on, before I do that, I should point out here that the HR breach model that was used in this project predates the zoned work, which I will come on to, so it's an earlier version of the model. The conclusions were that since the Simba model simulates head cut processes and the HR breach model comes from prediction of surface erosion processes, the best solution would be to try and come up with a model which combines head cut and surface erosion and internal erosion. Unfortunately, the project suffered some delays and it is still being written up. The work was completed 2 or 3 years ago, but Tony Weil at the US Bureau of Electrification in Denver is still writing the final reports. So you've had a sneak preview of the conclusions, and the report hopefully will come out in 2013. Moving on to the 2 models, Simba. What does Simba do, and the wind dam? Their approach was head cut is the primary mode of failure for breaching, which is fine if you're dealing with a predominantly cohesive, less erodible material. You need a mechanism for measuring erodibility, jet erosion kit, and their model basically develops or simulates the rate at which the step forms and the head cut moves backwards. Head cut formation processes, just a quick update, basically you'll get failure of the surface, you start to form steps, the steps cuts backwards, it cuts through the upstream slope, oh dear, hang on, through the upstream slope, and then you have lateral widening. So the Simba model basically replicates those processes. There are 2 versions of that head cut model. One is stress based and one is energy based, but at the end of the day it is a relatively quick model. Similar, I guess, maybe not as quick as Myron's, but the same concept in that it's predefined the erosion mechanism. It will fail, it will erode in this manner. It will erode down, it will erode back, and it will widen. The Simba model, when you hear that, is just relating to the mechanics of that head cut process. That sits inside WinDam, and WinDam B is released in the public domain by USDA, and that includes the reservoir itself and spillways and tailwaters and grass performance, obviously using the USDA grass performance instead of the Syria grass performance. So HR breach, I'll briefly cover the zone breach model, looking at head cut versus surface erosion, how erodibility of the soil versus the upstream stage volume relationship becomes important, and then the new zone breach and the implications that has on modelling. So here's the equivalent pictures for surface erosion. Starts off with overtopping. You start to see little steps forming. You think, okay, we're going to get a head cut, and then this flattens out, cuts down, and you can see that it's taking the surface of the soil off until you get to open breach. This is a far more erodible material than the head cut example that you saw from USDA. So what's the point here? Why is it so important? Well, it's all about when does the hydraulic control point erode. When you have head cut, you pretty much have steady discharge over the top of the levee because the crest isn't eroding until the point where it breaks through, and then you'll get sudden surge. When you have surface erosion, you get erosion of that crest control point as part of the overall process, so you get a progressive increase in release of water. So if whatever you're doing your breach analysis for, it becomes important to understand the shape of the hydrograph, then you should be looking at the dominant processes and more detailed modelling of this type. Nature of the flood hydrograph also depends on the relationship between the soil erodibility and the upstream stage volume relationship. So if you consider how the crest erodes, you have a competing processes going on here, and that's the rate at which that crest is eroding down versus the rate at which the breach can draw down the upstream reservoir level. And obviously the rate at which the crest erodes down is a function of the soil erodibility. So what you can get with the same embankment and the same reservoir but different soil erodibility is this. You can get a result like this, or you can get a result like this. So this is a situation where you have a more erodible material and it drops away, you have a hole, but the reservoir level is still high. You've got a high head of water, you get a very quick surge of water, and out it comes. This is the situation where you have a far less erodible soil, and the reservoir will draw down slowly as that soil erodes slowly. The volume of water released is the same, but this obviously would be far less desirable if you were living in a house just downstream of the dam. So what are we doing in terms of developing the model further? We were looking at a zoned breach model because most levees have been built, extended, modified. Embankment dams have different zones. So we wanted to look at what's the effect of having different soil types or different soil erodibility. It could be the same type but different erodibility. And it becomes very important. So here's just some screenshots showing two layers. You've got a top layer and a bottom layer. The top layer here is more erodible, so you can see that this section is eroding back more quickly compared to the bottom layer, and you've got the reverse down here, so the bottom layer is eroding back in comparison to the top layer. You'll find that you get those two curves I showed earlier. You can have this condition or you can have this condition. If you start bringing layers in, you might have one where it starts to follow this until it breaks through to the lower layer and then it follows this. Or it might start following the lower layer and then jump up like this. So really, if you've got a zoned embankment with different soils, you should be studying that effect, because you could be looking at a scenario of this or anything in between. Okay, to wrap up. So both Simba or Windham and HR breach zoned have continuing programs of development. You should be looking at what's your type of soil. Are you going to have head cut or surface erosion? Is it going to be initiated from overflow, wave overtopping, or internal erosion? The science supporting each of these processes is evolving, so the models keep stepping forward as the science is clarified. There is a need to avoid confusion regarding breach models and soil types. There are a lot of models presented ignoring the type of soil that they've been based on, whether it's head cut, whether it's surface erosion, and so on. There is a need to recognise that breach models are uncertain. There is no right answer. There is going to be a range of answers, and you're into uncertainty within your parameters, Monte Carlo simulation, and so on. There are various publications. Here's a few that have come out recently. New regression equations. That's just fitting data through historic failures. It's ignoring why it failed, what the soil type is. You've just seen the two plots I've shown you. So that regression curve could be including a very rapid peaky failure or a long drawn-out failure. Highly uncertain. NWS breach was 1980s model. This has been superseded. There are a number of things that we can do better on with that now. Back to regression equations here, highly uncertain. US Corps of Engineers has just integrated regression equations into HEC-RAS. They should be using AREBA. And so on. two last points. And this goes back to the discussion that we were having on Myron's paper right at the start. At the moment, we have levee stability analysis methods and models, and we have breach models, but never the two do meet. You either talk about, oh, it's about to fail because I've done my finite element analysis and it shows failure, and then you don't predict breach, or you say it's failed and this is what's going to happen when it breaches. We should be putting the two together. And then the second point is data. There's a real problem with getting access to good quality, large-scale, reliable data. The Dam Safety Interest Group project tried to address this and was successful to some extent. There's been some recent discussions about trying to collaborate, coordinate and share at a European level, and I would encourage all of us to try and do that if possible, and also to do so at an international level. Anyway, I'll stop there.
Thank you, Mel. Once more. From the previous presentation, I had the idea that failure can start after 1 hour, maybe 2 hours. Just now you mentioned 12 minutes, 20 minutes, 25 minutes. What is the reason that I would expect this last expectation, because I had the experience with failure during 15 minutes roughly.
Yes. Depends entirely on the material and the situation and the initiation mechanism, I think. It's it would be wrong to say one or the other.
Yes, but you used in your previous presentation roughly 1 hour.
Ah, yes. So the grass.
Your
yes.
colleague also as well. 2 hours roughly.
This is because the grass performance curves from Syria ignore the time zone 0 to 1 hour. They just start from 1 hour onwards, and I think this is probably because the test data originates from grassline spillways from dam overtopping rather than levees. And they were probably assuming, I'm guessing here, they were probably assuming that if the dam was going to overtop, it could do so for an hour or so before they needed to worry. But
okay, certainly,
yeah,
there have to be some changes. Yes. Please, question from the floor. Yes.
Yes, well, I don't know if this is obvious or implied in this kind of models, but do these kind of models also consider the availability of water? Not the water head behind the dam, but the availability of water. So it's not the same having a small reservoir than a big one, in the sense that the water head will fluctuate quicker in one than in the other one, right?
Yeah, it depends how you use it. So the HR breaches, you can either have it as a standalone where you simulate the entire reservoir. It's a flat pond model, but it allows you to draw down the volume of water, or you can have it integrated within a flow model like InfoWorks 2D, and therefore it's taking whatever water is being simulated in the flow channel. Is that your question, or did I miss the point?
It's more about, like, if you have a small reservoir, what I think,
yeah,
you will have the same height, let's say the same water head, but the delta between, let's say, time steps will be quicker.
Yes.
Quicker, so then the rate of erosion will change as well.
Yes, well that's what I meant by stage volume. So it's the rate at which that driving level will reduce as the flow volume goes through the breach. And if you have a small reservoir, that will go down very quickly. Yeah, so a small reservoir is likely to give you a sort of flatter, less peaky. Well, you might have a little peak, but then you've drained it, you know.
Okay, thank you very much. So, thank you.